All right, let's make sure the audio works on this. Beautiful. What side of the board are we on? Yeah, on. Okay. Sweet. All right. Hill. My name is Justin Hill, and I'm gonna be and my son, my man Joel is back here. You guys can see him. But I'm gonna be your teacher, your professor for this 5 weeks. So this is Calc 2, Summer 2, just a 5 week class over Cal 2. Oh yeah, 2025. So I'll be your teacher for the next 5 weeks. 5 weeks is fast. So the first thing I just want to say really quick is we are gonna have a ton to do every week, or you're gonna have a good bit to do every week. I'm not saying that's bad. I'm not saying that's impossible. I'm just saying buckle your seatbelts, get your kind of mind in gear for that, because that is the only that's what we're gonna be doing, and that's unfortunately the only way it happens when we do kind of a 5 week class like this. So you guys would have you already finished the orientation module. So for you now, you should see week one should have popped up for you already. And week one is a good kind of encapsulation of basically how every week is roughly going to go roughly in this class. So week one, what you should see now is you should see a week one lectures page, and that'll have all the lectures that you guys need for this week. And then you'll see 4 little pages for the homework this week. So as you guys kind of know from the welcome message that I sent out and from going through that orientation module, that your homework is done. So your homework is done in Cengage, but the way you get to Cengage is just clicking on the little homework buttons, the little load buttons. So again, in this week's module, you'll see a page for 5.1, 5.4, 5.5, and 5.7. You'll just click on those pages, hit the little button, and that'll pop up the homework for you. It's kind of not only the quickest and easiest way to get in there, but maybe the best way to get into Cengage. And that's all you're using Cengage for, by the way. So Cengage is just for you to do the homework, also for you to have, again, in the orientation module, you guys saw you have that little button that loaded the ebook for this course. So it's also for you to have access to that ebook. I'll kind of talk about it, I'm sure, a couple times in this class. Maybe you've never, like really used or read a textbook before for your classes. Maybe you have, but if you haven't, the textbook is hella more useful than you would ever expect. So it's one of my small little underhanded goals in my classes is to get y'all to kind of jump back in to invest back in to honestly to reading text. So I'm not saying like you need to read the whole thing and everything needs to make sense, but there's a ton in these sections that the author puts in there that is actually really helpful for you to make connections with the ideas that we're talking about, but also make connections with the ideas that you'll need to then do the problems that you're looking at. Again, I'm your teacher. I'm going to do all that on this board. You'll see that I'm going to use problems from the book as fodder, but you'll see the way that I teach is I teach the subject, I teach the idea, I teach the content, and I'm going to get you guys to connect to it, understand it, have it make sense of the work that you're doing, this homework that you're doing. One of the biggest things I can emphasize more than anything for a class like this, I'm sure you guys have already seen this at this point in your kind of STEM major and STEM career, is that mathematics is not a bunch of homework or a bunch of problems. Mathematics is a tool. You are learning these ideas that we're going to learn in this class. You're going to learning the ideas and concepts behind them and the patterns behind them as tools to do something. In this class, it's tools to do the homework, but honestly, that's not even really the end point. Once you're done with this class, you want to master the ideas and the concepts that you're learning here, and the patterns that we're learning so that you have tools to do your science and engineering that you're doing. So to do, actually for this class, it shouldn't necessarily be biology. Maybe there might be some bio majors in here, but to do your chemistry, to do your physics, to do your mechanical engineering, to do your electrical engineering, etc. These are tools for you to figure out things about reality, to figure out things about that engineering problem that you're looking at, that design, that circuits, that chemical reaction. That is what these are for. And so when I teach, I major on getting you guys to really understand the concepts and the patterns and the ideas and really connect to that, so that you have tools that you can use. And also, again, underhandedly, even the way that we're going to go through the problems, the way I'm going to get you guys to go through these problems is all thinking based. I'm going to get you guys to think about what's the next play that I need to do. What's the tool? What's the pattern, the concept that I'm going to need to use to get to the next place in this problem, and eventually to get to the end of the problem. Because that's actually how you do engineering and science. You'll see once you get into a lot of those engineering and science classes, you're rarely going to see a problem that looks exactly like something you saw in this class. I mean, you're going to see it's going to look, when I say looks exactly like, now you're going to see problems that look a lot like the problems we see in this class, but you're never going to see something, or rarely ever, that looks exactly like a problem in this class. And that's actually how the real world in science and engineering works. The real world is at some sense, at both times, the patterns are simple, but the application of the structure of the play is way too complex for you to ever see to expect to see an exact repetition of something that you see in a class, right? Because a class is just a microcosm, right, of this large thing. So how could you see a ton of, everything that we teach in the class be an exact replica, the macrocosm. Sort of getting off track here, but we'll keep going a little bit. But if I can get you guys to really major on understanding really thoroughly understanding the concepts, the patterns, and if I can get you to, when we do the problems, to major on not what's the procedure to get through this problem, but how do I think my way through this problem? How do I take the things I know and use them as tools to get to the end of the problem? And what I promise you is then when you get to your STEM classes, when you get to your engineering classes, and then when you actually get out into the field to your job and doing, have some engineering or science problem, like design, structure, whatever that you're trying to solve and figure out, you'll know how to think your way to that solution, and you'll know the things you need, the patterns, the concepts and ideas, the derivatives you did in the last class, integrals in this class. You're going to know the tools you need to get to the end, and how do you think your way through the problem and use those tools to get to the end. And that is actually the point. I would say, again, the point of this class is to teach you guys about integrals and to teach you guys about all the stuff in Cal 2. But actually the point of this class is to teach you how to solve problems that way, and to use the tools that we teach you in this class. Because that's actually what's going to get you not only through your major, but that's actually more importantly what's going to get you to do your job when you get out of all this. And some of you probably, maybe you already know how to do all that, but that's really my goal. My goal is to actually teach you how to think and work like that. And so I'm going to do that by teaching you guys Calculus 2, and you guys saw Calculus 1 basically was all about derivatives, right? So you started with limits as a little, not only precursor, not only prep, but limits ended up being the idea you needed to understand fundamentally how to get the derivative. But then the derivative ended up being this idea of basically the slope of a curve. And it was an ancient problem that they've been trying to solve for thousands of years, how to truly find the slope of a point at any point on any curve. And we finally figured it out in the 16th century or 17th century, in the 1600s. Both Newton and Leibniz kind of figured that out. So there's another ancient problem that we've been trying to figure out for thousands of years. And that problem was, how do you find the area under a curve for any curve? And so that's what you'll see most of calculus, the end of calculus 2 is about, is we want to try to solve this other ancient problem, which is how do you find the area under any curve, not just the nice ones, right? So not just the nice shapes and curves that you see and in Euclidean geometry, kind of your standard geometry class. But any of them, all the wiggly stuff that doesn't have, great definition or a great shape that we have a, really nice formula for. So that's what we're gonna do in Cal 2 is we're gonna solve that, is we're gonna figure out that problem. And the thing that solves that problem is gonna be what we talk about for most of this class. And then towards the end, we're actually gonna get back to, we'll talk about series and sequences. And so you'll see, we're again gonna be using this new tool. So by the way, so this new tool is called the integral. So, again, an ancient problem, trying to find the area under a curve, and the solution ends up being something called the integral. And again, Newton and Leibniz in 1600s figure out the integral as a solution to this old problem. And that integral then becomes a way, so we'll go through, as we go through this class, you'll see, we're gonna figure out how to do the integral, and then we're gonna use it to find areas, because that is its main purpose, that's its main thing. But then at the end of the class, we're gonna look at series and sequences and find that the integral, along with the idea of limits, going back to the beginning of your calculus journey, ends up being the key concepts we need to figure out some things about series and sequences. So that's kind of where we're going to go for the class. So we're going to start by learning what the integral is, or learning about the integral. Again, I'll go through it in these lectures, but fundamentally it is the solution to an ancient problem. How do you find the area under a curve? But we'll learn what the integral is, and then just like you did with derivatives, once you learn the derivative, then you learn some patterns for how to do some pretty common derivatives, right? So we'll do the same thing. We're going to learn some patterns for how to do some pretty common integrals. So we'll focus on kind of how you do the integral. And then we're going to use it for area. So like I said, that's its main purpose. And then we'll end with going back to limits along with integrals to look at something called series and sequences. So that's what we're going to do here, and you'll see too by the time we get to the end of Cal 2. Cal 2 and Cal 1 in my mind are kind of like an ellipse, like they're, so you end up at the beginning, you end up with a very round set of ideas and concepts. The ideas of limits, which you need to do the derivative and the integral. But then the derivative and integral, that's actually the star. That's the two main things, honestly, with calculus. So calculus takes all the old functions that you know and basically says there are two new operations we can do with these things. We can take a derivative and we can take an integral. And then kind of goes over then you just kind of look at all the uses of a derivative for a function and the integral function. So anyways, so let's get started today. I've titled this lecture integrals or kind of by inverses. So like I said, integrals are about finding the area of a curve, but still, even with that known, there are two ways that I want to kind of talk about integrals or introduce integrals to you. And so today we're going to talk about it as an inverse. We'll get to what that means. But I want to start by talking about it as an inverse. Then our second lecture, we'll get to that idea of looking at the area under a curve. But let's start with integrals as inverses. Let's see. So I want to start with, since you finished with derivatives in Cal 1, I want to start with derivatives. Start with the idea you already know. And let's just kind of talk through, get a setup going, let me talk through that setup and some ideas. So for instance, don't even need to leave the numbers. This. In sense. So I'm gonna do here first. Yeah. Um, So the way I want to start this, again, like I said, let's start with some things you already know. So let's say I have a function, and what I'm going to start with, we don't know what the function is. But what I do know is that if I take the derivative of that function, that I get, start, I get something like maybe 3x. So there is some function, I don't know what it is, but I know that when I take the derivative of it, I get 3x. So since you guys know, it's like, you know how to take a derivative. So notice what I'm doing here is I'm starting with, I'm not even really having you take a derivative, right? I'm just telling you the result of the derivative. So you can almost think of it about this like an kind of a process diagram, error diagram, something like that. I start with the function, I do an action to it, and this action is the derivative, so I'll just use little, and the result is 3x squared. So the first thing we want to figure out is if I needed to figure out what that function was, if I need to figure out what I started with, so that when I took the derivative, I got a 3x squared. And again, I've given you guys no technique. What I'm saying is what you already know from calculus 1, you can do this. So the question is, what I want you to do, or what I want us to figure out, is if the derivative of a function is 3x squared, the question to you is, how would you go back and figure out what that initial function is, where we start? And I'll give you guys, I know I obviously can't hear you on this video. I still want you to think about this and basically shout an answer at the screen. And then, I'll kind of talk through what I hope are your thoughts on it, and then kind of what my thoughts are. So go ahead and take a second, think about it, and just kind of shout at the screen. How would you go back and find the function we originally started with? Bum, bum, ba-da-da-da. Ma, 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 ba. Yeah. Um, all right. So how would you go back and find that initial function? And maybe hopefully one of the things you might be thinking here. So again, the advantage that you have is you've already done Cal 1. You know how to take a derivative. And if you think about the derivatives process, you start with function, you end with a result. Again, in Cal 1, what you did is they would give you the start, the initial, and you would work to get to the end. But again, the advantage you have is you've seen these enough that if you know the end, you could probably guess how you got to that beginning. You basically can sort of guess what function you started. So notice that the end here is, so in terms of thinking about the types of functions that you took derivatives of and got results from in your Cal 1 class, this is a power function. So you want to think about when you did a derivative, in Cal 1. How did you take the derivative of a power function? So think about the derivative on a power function. This will be let's remind ourselves just some general how we find the derivatives on some different types of functions. So we had power functions that we took derivatives of. And what we did there is, let's say you had x to the n power. What you then would do when you take the derivative, you end up with n times x to the n minus 1. So this is kind of the formal way to say this. You'll see as we go through the class, I actually, even though I'm a mathematician, I've published research, I have citations on my research. Especially when I teach this, I actually shy away from kind of formal ways to write this. Because I do think that for this level of class, when you're looking at this, if you're not a theoretical mathematician, the formal way to write it kind of like when you're reading it, you constantly have to interpret what it means. And so it actually doesn't help you a ton. It doesn't read well, basically. So actually, so x2, let's do x to a number. It's gonna be that number, so you multiply by that number down the front, and then instead of saying n-1 or something like that, I'm gonna do this. I'm gonna say it's x2, one less than whatever that power was.
Right.
This is maybe a more informal way to write this, but maybe makes more sense when you read it. When I take the derivative of the power function, what I always do is I multiply by that power, and I make the power one less. So like I said, the advantage is you already know that as a forward process. So that means if I know the derivative is 3x squared, all I got to do is work that process in reverse. So if I want the original function, if I want f of x, then all we got to do is kind of do this process in reverse. And what would this process be in reverse? So that process would be, so again, this process, you want to think about it in two steps. I multiplied by the original power, and I subtracted one from that original power. So you literally want to do the opposite operations there, and you want to do them, and you want to do it in opposite order. Like last thing that was done is the first thing you want to undo. So instead of doing my power one less, I want to bump this power back up one. So I'm going to add one to my power. And then instead of multiplying by that new power, I'm going to divide by it. So add one to the power, then do this, add one power, then we're going to divide by the new power. So again, the last thing that was done on the derivative is the first thing that I undo. So instead of one less, it's one more. And then I divide by the power instead of multiplying. So to get f of x, I'm going to bump this power up to the third, and then I'm going to divide by that power. And what does that give? So it gives you x cubed. So what I'm saying is the original function should actually be x cubed. And notice that makes sense. So if you start with x cubed, again, if you think about this in terms of a derivative, if you start with x cubed, and I ask you to take the derivative, you would multiply by 3. That gives you the 3 there. And you would bump the power down 1. You would get x squared. Good. So the derivative is indeed x squared. So this should be our original function. Now, the one thing that this reverse, I'm calling this right now, this reverse process, the one thing this reverse process doesn't do for us is we also know from Cal 1 that if you have a constant, if you just have a solid number, so if you have a solid number and you take a derivative of it, what does that give you? Good. If you have a solid number and you take a derivative of just that number, you get 0, right? So the one thing that this process doesn't take into account is there could have been this, you originally could have had plus or minus a number here, and you wouldn't really know after you take the derivative, because the derivative of a number is 0, which means when I take the derivative and I get 3x squared, but that 0 doesn't show up here. We never write it there because we don't need to. Anything plus 0 is just whatever the other thing is. So there's there could have been, instead of x cubed, there could have been x cubed plus or minus a number. So what the way I'm going to write this here is the way they write it in the book, where they write plus c. I don't mean that it's definitely adding a number. I'm just saying c is just some constant. Could be positive, could be negative, it could be adding, it could be subtracting. But either way, what I'm saying is there could have been some constant originally that, unfortunately, after you take the derivative, it becomes a 0 and it just goes away. So if we're looking at the derivative, we know the derivative is, we just don't know if there could have been a number to begin with. So in general, then, if f prime is 3x squared, I'm saying f of x is x cubed, because that undoes the derivative, plus or minus possibly another. So I get they have a term for this. You'll see it in 5.1 and 5.4 when you read through it. But that's all this is. Just it's basically an extra kind of constant to be, a general. They call it I think they call it constant of different of integration. But it's just a general constant that we put there in case there was a whole number, there was some number there. Okay. So overall, what I'm saying is if your derivative is 3x squared, then your original function has to be x cubed plus c. And so a couple things that I want to know about this. So what we're doing is we're seeing the end of differentiation and we're trying to go back, trying to undifferentiate it. So there is a word for undifferentiation. That word is integration. So like I said, the second part of calculus, basically almost all you'll see is basically all about integration. Integral is the second major operation, second major tool that not only you learn in calculus, but that basically was invented when calculus was invented by Newton. And I would actually argue. So again, by the end of this class, you'll see that that's pretty much it. Honestly, calculus is taking a derivative and taking an integral. And the nice thing is it ends up the integral is just the opposite of a derivative, just like addition and subtraction are opposite, just like multiplication and division are opposite. So we're literally saying derivative is this new operation that you learn that you can do with functions. That's a forward process. There has to be a backward process, and that backward process is called integration. So you're going to start with something that is a derivative of some, a previous function, and you're going to work your way backwards. And we call that backwards process integration. So this is called the integral of this original function. So the term you'll see in this section, so this basically, this work that we're doing corresponds roughly to section 5.1. The term that you'll see there is they call it the antiderivative. So mathematicians are not clever usually. You did a derivative, the opposite of it. Anti is just a prefix that means opposite, right? So they call it the antiderivative, but then they give it a more specific name, and that name is called the integral. So what I want to show you is just a couple different ways that you can write not only what we just did, but write what I just named. I just named this as the integral of this initial this initial function. So all right, so the way that you'll see this written often, we kind of reshape this over here. So the way that you'll see this written often is you'll see, so the symbol for integral is this kind of stylized, funky, elongated S, right? And in the next lecture, you'll kind of see why it is sort of like an S, like it does come from the alphabetic letter, alphabet letter S. And you'll see why in the next lecture. But it's kind of this long stylized S. So the way that you'll see this problem often written is something like this. So the integral of 3x squared. Sorry guys, I missed. We're gonna put come back, but I do want to, let me bring in something else also first. So this initial equation I gave you. Or the initial equation I gave you there, I wrote it as f prime of x equals 3x squared. So one thing I want to note about this equation. So this equation tells you a derivative is equal to something. So most equations that you solved before Cal 1, your pre-cal, college algebra, whatever, they were equations that would tell you what f of x is, right? That would tell you what a function is. This is the first time you're seeing an equation that tells you what a derivative is. And there's a name for that type of equation. And so the only reason I want to give you this name is because you'll see it in the homework and because you'll see it in a later class. But when you have an equation that tells you the derivative, or at least involves the derivative of a function, so it doesn't tell you what the function is, it tells you what the derivative is, that equation is called a differential equation. This is a differential equation. It's an equation that involves derivatives. Now I wrote it this way for you, f prime of x. You guys know from Cal 1, there's several different ways there's literally just other ways that we could write this symbology here. You could write something like y prime equals 3x squared. This another way we could write this. You could rewrite y prime or f prime or whatever as dy dx. And I want to sit on this way of writing it for a second. So this is more conforms to the way Leibniz would write, derivatives and stuff like that. So you can write it as dy dx equals 3x squared. Now, one of the advantages of Leibniz way of writing stuff is then dy and dx then sort of become actually variables, basically. They're placeholders they're placeholders, they're variables, which means I could multiply both sides by dx. I could rewrite this equation this way, dy equals 3x squared dx. Now, why would we do that? Or why am I even bringing this up? So again, what I did to begin with is I started you with this differential equation. I told you what the derivative is, and then we figured out what the original function was. And I told you that that action of starting with the derivative and moving your way back up to the original function, well, we have a word for that, and that word is the integral, or to integrate. So integration is the opposite of finding derivative, the opposite process. So the way that they're going to write the integral is using this integral symbol, or using this elongated S symbol. So what I want to show you guys then is we use this integral symbol to show that we're going to integrate, that this is my derivative and I'm going to work my way back up to the original function. And if y prime is the derivative, then the original function is y. And you guys saw that was the way it was written all the time in Cal 1. So the integral of dy is y. So I guess what I'm trying to say here, I'm trying to show you guys kind of why, trying to show you guys why when they write an integral. So when you write an integral, the way you're going to see it written almost every time is that this is my function that I'm integrating, that I'm trying to find what it started as. But you're going to need to have this dx here. So they're always going to write this dx here, so that basically the math of this corresponds to this dy dx way in writing the derivative. This is the way you're going to see it written all the time. So this is then, we could say, is technically our first problem. Y, and we don't even have the y's. But y equals the integral of 3x squared dx. I want you to find the integral of 3x squared dx. And my answer then is exactly what we found there, x cubed plus c. Oh, I still explain that here, but I apologize. So that's what an integral is. An integral is undoing a derivative. It's the opposite of a derivative. And if you have a power function, it's pretty easy because again, you just got to remember how you take the derivative for a power function and just reverse the process. So add 1 to your power and then divide by that. I want to do some more problems like this, so they'll give you, yeah, we'll basically start taking some integrals. I just want to write a lot less here. So again, everything I've written up here, if you want to copy that down, that's fine. That's not actually what you're going to write out for any of these problems, but it's my way of getting you guys to connect with what you saw in derivative 1 and calculus 1. So that you kind of see why these are written the way they are for integrals. So let me go back. One erase. What I'm going to do here is, we talked about this. I take the derivative power function from what you guys already knew. So I want to then have a similar mirrored. I'm going to have a mirrored summary for integrals, taking an integral for the same types of functions. Just summarize what we just did. So then for a power function, when you take the integral, so if I have x raised to a power and I take the integral, then I'm going to do basically the reverse. So I'm gonna, like I said, we're gonna do 1 more of power. I'm gonna then divide it by that 1 more of that number. Hopefully that makes sense to you guys. It's a way to write that. So if I'm dealing with power functions, you knew from last semester or whenever you took Cal 1 how to take the derivative. Now you know how to take the integral. All right. Let's see. So what I'll do is, let me give you a couple problems, just the way they're written in the book. So let me find a couple problems in the book. Let me have you guys start taking the integrals here. Uh, Give me a second while I find these problems. Yeah. So, let's write a couple more of these. We'll do these in kind of 2 different ways. We'll write a couple more of these differential equations. So we'll start kind of like that and how you solve it. And then we'll go to writing them like this using the integrals. Also, really quick, you guys don't have to do anything with this, but I'm gonna change the way I wrote this just because it looks better this way. So if I want the derivative of a power function, that's what I do. And if I want the integral of the power function, then we just do the reverse, right? All right, so so I'm going to ask you to solve these differential equations, which means you're going to be integrating. You're going to be working this backwards. So Right now, we're thinking about power functions. We did the derivative was 3x squared, and we worked it back to x cubed plus c. What about if what about if f prime is x to the 3 halves? That's still a power function, x being raised to a power. So we want to do the same thing then. We want to bump this power back up one, and we want to divide by whatever that results. So again, basically what I'm going to do is I'm going to integrate. So I want to give you guys a second to do that. So the way we'll do this, again, obviously this isn't live and I can't really interact with you guys, but the way we'll do this is I'm going to pause on my side of the video, you pause on your side of the video, see if you can work this integration, kind of work this backwards, and then unpause the video and magically my side will be unpaused as well, and we'll work through the result, see if you get the same answer. So go ahead and pause your side. I'll pause my side and go and work on that for a second, for a minute. All right. And we're back. Okay, so again, to integrate, to do the opposite of the derivative, we need to bump this power back up one. So if you take 3 halves and you add 1 to that, what do you get? So what you should have got here is 5 halves. So 3 halves plus 1, which is 2 halves, is 5 halves. Or basically 1.5 plus 1 is 2.5, and 2.5 is a fraction, it's 5 halves. A note really quick that you'll see not just for this problem, but you see all throughout this class. This is, higher mathematics is about exact solutions. Now in this case, 5 halves is exactly 2.5, but in general, decimals are not usually exact solutions. There's some sort of you're rounding, or there's something like square root of 2 or pi, right? That the decimal never ends and never repeats, so when you round somewhere, or even for solutions that do have repeated decimals, we usually round somewhere. But rounded numbers are not exact solutions. So in this class, I want exact solutions. That means I don't want decimals. Unless we'll see some problems. So basically, occasionally they're going to ask you for the approximate, the approximate solution, and that's when they want decimals. I'll tell you where they're round. But other than that, we want exact solutions. We're a math class. We do not want decimals. So when that means I want fractions. That means I want square roots. That means so all those symbols that are that we say are the exact solutions that we know are the exact solutions. I want those. I don't want decimals. So it'll be x to the 5 halves power. And then I have to divide this by 5 halves. But when you divide by a fraction, what essentially do you do? You just take the fraction, flip it over, and then multiply. So what I'm going to get here, f of x equals 2/5 x to the 5 halves power. And then again, remember we have to add on this constant of integration. We have to add on a constant because there could have been a constant to begin with, and we wouldn't know because when we take the derivative, we get 0, and we never write 0. So 2/5 x to the 5 halves plus c. And that would be the solution to that differential equation, but that would be your integral. So if x to the 3 halves is your function, the integral of it is 2/5 x to the 5 halves plus c. Let's do another. So part of the reason I want to do this problem is because I want to remind you, just kind of jog your mind that we can have fractions as powers, but we can also have as powers. So let's say f prime of x now. F prime of x is. Let me just to give you some variety in the way they write this. You also see this in the homework, so we could write it as dy dx. It could be something like maybe x to the -4 power. So now I'm saying the derivative, now my differential equation says the derivative of x of -4, and I want you to figure out the original function. So again, we're gonna have to integrate. And again, this is a power function. So I'm gonna add 1 to this power and then divide by whatever that is. So what we'll do is again, pause on your side, I'll pause on my side, go ahead and work that through really quick. Check that we're getting the same answer. Let's see what you got. So if you add 1 to -4, what does that get? Good, that should actually be -3. So my function here should be x to the -3, but then I have to divide by that -3. And then plus c. The overall, so then the question is overall, how do I write this? Roughly something like this. So -1/3 x to the -3. You can also write it as x to the -3/3. That doesn't bother me either. I like fractions. I kind of like to write fractions out. Plus c, and that is your integral. So again, I mean, it doesn't really matter how you write these things at the end, whether you use f of x or y, but notice sort of in terms of syntax, the way they're doing this, if they started written f prime of x, they're gonna write the functions in f of x. If they started written as dy dx, they're gonna write it as y. Again, it doesn't matter how you do it because they both mean the same thing. So in terms of your work that you're doing for me, doesn't matter. But I do want you to see sort of what they're doing there with the language of this, the syntax. Good. So either way, what we're doing is we're taking an integral. So they might code it as a differential equation. But more often, the way they're going to write this, they're not going to write it as a differential equation. They're just going to write something like the following. So let me put a couple more columns up here. So more often what you're going to see is maybe something like this. They're just going to ask you to take the integral. And again, on the next lecture, we'll talk about this technically what they call the indefinite integral. Talk about the definite integral on the next lecture. But the integral of maybe let's do something like 5x to the third minus 4x squared plus 2x. Yeah, so this is the way they'll generally write this. So when they're asking you to take an integral, most of the time they're actually going to write it this way. So they want you to take the integral of this function, and they put the dx there again because we technically need that symbolically. We need that to be able to do the integral to get to y. But this is the way they're going to write it most of the time, and they're just saying take the integral of this thing. Now, I want you to notice what we have here is not just one power function. We actually have several power functions added and subtracted together, which we otherwise know as a polynomial. But like you guys saw in, so in Cal 1, what you saw is if you had to take the integral of, if you had to take the derivative of a polynomial like this, you just work each part. So as long as your parts are separated by addition or subtraction, not just for a polynomial, but for any function you're looking at, you can take the derivative of each part and just slap them together, just add, subtract them together. Since integrals are the opposite of derivatives, right? So they're the same process in reverse, then we're going to see the properties of integrals are either exactly the same or very similar to derivatives. So basically the patterns that you can do with derivatives, you should be able to do with integrals in reverse, because it's the same process, just in reverse. So if I was going to take the derivative of this, I would just be able to do each piece. We could do the same thing with the integral. I want to take the integral of this. This is a polynomial, yes, but this is just 3 different power functions, and you just got to take the integral of each piece and then just slap them together. So again, same pattern, same column properties, but same pattern that you saw with derivatives. So that's all you got to do for this one. You've now got to take the integral of 5x cubed negative 4x squared, 2x. But again, these are just power functions. So you're going to do the same pattern, same play. Add one to the power, and you're going to divide by what that result is. So let's see if you guys can get this. So go ahead and pause on your side. I'll pause on my side, and let's see what you get. We'll start with the 5x cubed part. So I'm going to bump the power up 1 to 4, and then I'm going to divide by 4. So what we should get there is, and actually give me a second in terms of how they're writing this. Let me see if they're writing an F or a Y or what are they? Really doesn't matter. Yeah, they're not even doing that. Okay, yeah. Good. So that's going to be then, so we're going to have x to the 4th power, but then I'm going to divide by 4. And so I'm simply going to write that as a fraction. So again, you can write it as 5/4. You can write it like this. Again, what I'm saying is, since we want exact solutions, get very comfortable with writing things out as fractions, as square roots, etc. Take those symbols as what they are. Make some art out of it. So good. 5x to the 4th over 4. 4x squared. I'm bumping the 2 up to a 3, and then dividing, so that'll be minus 4/3 x cubed. And then the 2x, I'm bumping this x technically has a 1 there, so that bumps up to 2. You divide by 2, so that'll end up being plus x squared. And again, we don't know if my original function had a constant there, so I'm going to add a constant to it. And you've got it. That is the integral of 5x cubed minus 4x squared plus 2x. I would say, is there any questions there? I wouldn't be able to hear your question or answer it, so quite good. So let's do a couple more problems. Fill along this power function line. We just saw two problems, these two problems 2 and 3. We have fraction as power, we have a negative number as power. So what I want you guys to just think back and tell me is, I just kind of call back up, is so a fraction as a power, what does that actually correspond to in terms of functions? What type of function is that? Good, so hopefully remember that at least the bottom of the fraction actually tells you the root. So when I say something like 3/2, what I mean is square root to the 3rd power. Good. So let's look at we're going to do some problems with some roots in them, and all you got to remember is the roots actually, the first thing we're going to do is we're going to turn that into a fractional exponent, because that's what it actually means. And then also this negative exponent, what did that actually correspond to? Good. So that corresponded to actually dividing by x to that power. So for instance, so what I'm saying is, let me just kind of, remember that x to the 3/2 power, another way you could have wrote this is the 1/2 means square root. So this could have been square root of x to the 3rd power. Or you put the 3 inside, doesn't matter. Because of the properties of exponents, it doesn't matter. So square root of x cubed. So this x to the 3/2 actually means this. And it's the same both ways. It means the same thing. It's just, one is written in German, one is written in Spanish, right? It's just different language, but it means the same thing. And this x to the negative 4, that actually means 1 over x to the 4th power. So remember that your negative exponents really correspond to x being raised to a power on the bottom of the fraction. So it corresponds to a very simple rational function, but it corresponds to a rational function. So one of the nice things about power functions in general is, at the least, they definitely correspond to polynomials, but they also correspond to quite a few other types of functions that we've seen. They correspond to root functions, correspond to very simple rational functions. So they cover a lot of types of functions that we've seen. And again, you guys saw this with Cal 1. Hopefully, you at least saw it when you were doing the work. And hopefully your teacher made a point of making a comment on that when you're learning how to take the derivative of power functions, you weren't just doing that to learn a process, to learn a procedure, to do some homework. You were doing that hopefully realizing that Now you had a tool that works for a ton of different types of functions that you've seen. So derivative again is you'll see as you go through your classes is one of the major things that you need to do in science and engineering to solve a lot of the mathematical work that you're looking at. So it's a major operation that you need to be able to do. And by knowing how to do that with power functions, you now know how to do that for polynomials, you know how to do it for root functions, and you know how to do it for simple rational functions. So also now, so again, hopefully that just hit you when you were taking your Cal 1 class. Oh crap, now I can do a lot of shit, basically. I have a tool that helps me in a lot of situations. So the same thing here. Now I can take an integral, not just of simple power functions, but of polynomials. I can do roots. I can do simple rational functions. Let's do a couple that kind of mirror these two here. So let's do maybe the integral, and one like that, that's fine. Let's do maybe the integral of do cube roots, maybe x squared dx. And let's do the integral of yeah, Perez how it's maybe 1 over do 1 over x to the 6th power. So and dx. So to find, I want to take the integral of this. And again, at first this looks like, okay, what in the world do I do with that? It does not look like a power function. But the secret is it really is a power function. So we can rewrite this setup as, and I'm saying this, I know you guys already know this, but I'm just trying to get it to connect and jog with your memory. If I'm saying too much basic stuff, just ignore me for a second and go ahead and write out the word, figure out the answer. But we know that x cube root of x squared, how would you rewrite that as a fractional power? Good. That's going to be x to the 2/3 power. So cube root, so it's a 1/3, it's a third, and then squared, so 2/3. That's going to be that integral. And then really quick on 6, 1 over x to the 6th power, how would you rewrite that? Good. That's going to be, we're actually doing the integral of x to the -6th power. And then you can rock and roll. So, basically the lesson out of this is just, and you did the same thing when you did the derivatives. So you get something like this. If you can rewrite it as a power, yes, rewrite it as a power, because then you can use your power function pattern, and that gets you a lot, that gets you very far, very quick. That gets a lot of these problems. So this is why when you're doing Cal 1, you learn derivatives, they emphasize that you did so much with power functions to begin with. Because again, secretly, this actually solves, the patterns with power functions actually solves a lot of issues that we're looking at in running, or a lot of functions we look at in running. Okay, I'm talking too much. So you guys, we have each of these rewritten as powers now, and then you can do the integral work pretty easily from there. So you pause on your side, I'll pause on my side. Go ahead and work both of these. We'll come back and make sure you're getting the right answer. We can get, so this x to the 2/3, and we want to bump that up by 1. So now we're adding 1 to it, but you got to do that in terms of fractions. You're really adding 3/3 to that. So what we get is that's going to be x to the 5/3. And then you divide by 5/3. Kind I'll write that here. But we know dividing by 5/3, so dividing with a fraction just flips that fraction. And this is all gonna be plus C. So when you write this answer, now again, for me, it doesn't matter how you write the answer. And I think for Canvas, or not Canvas, Cengage, it's not gonna be a big deal. But again, notice they give you the function in terms of a root to begin with. So it's kind of like if we start there, we kind of want to end there. So I'm not saying you have to. So I guess let me be more. Let me just kind of write more and say less. What I'm saying is you could write the answer as 3/5 x to the 5/3 plus C. This is mathematically correct. But on your homework, just watch out. They may, by giving you the root to begin with, they basically may be saying they want you to write the root at the end. Just look at on the homework. They usually say how they want the answer written. So another way to write this would be 3/5 cube roots of x to the 5th power. Just know that both of these say the same thing. Again, like I said, this is German, this is Spanish, different languages, but they say the same thing. But either way, this is our answer. And to number 6. So it's -6 plus 1 is a -5. So this should be x to the -5 power. And then you're dividing by -5. All plus C. So again, the ways you could write this, I might write this as negative x to the -5 over 5 plus C. That is one way to write this. But again, just look on your homework on a problem like this to see if they don't allow negative exponents. If they don't allow negative exponents, then all they're saying is if you started with the negative exponent interpreted or written as in the fraction form as 1 divided by, then you just want to kind of you want to write it in that form at the end. So you could also write this as -1 over x to the 5th, or sorry, 5x to the 5th. Plus C. So again, both of those are correct. They both say the same thing. So either way. All right, good. Let's do one more. One more along this power function trail that we're going on. Let's just mix everything in, throw everything in. So maybe let me have you take the integral of we do 6 x cubed minus 3 square root of x plus maybe 2 over x cubed. So again, like that previous problem I had here, as long as, just like you did with derivatives, as long as it's separated by plus and minus, you just do each part separately. So this is just sort of 3 mini problems in one. But again, they're all, they're all power functions. You're still using the same pattern for all. All right, so I'll let you see if you can work your way all the way through this. So go ahead and pause on your side, I'll pause on my side, and then we'll come back and work it through. And you are back. All right. So again, each of these, I literally am just going to take each of these sort of separately. I can sort of, with each of these, I can sort of, in my head, I can have the powers written out in my head. But I do wanna show that to you guys. So we're doing the integral. It's gonna be 6x cubed. This is gonna be minus, this is really 3. So there's a constant in front, which, so again, going back to derivatives, you guys know that when you have constants multiplied by something you're taking the derivative of, the constant just stays there, right? So again, integrals are the opposite of derivatives, so we should have the same pattern, the same, just same pattern there, and we do. So when you're taking the integral of something like 3 times the square root of x, is again, as long as that's times, then I'm just taking the integral of square root of x and then slapping 3 on, right? And the same with this 2 over x cubed. I'm really taking the integral of kind of 1 over x cubed with a 2 in front. And then I'm just gonna slap that 2 on at the end, 2 times in front. So again, that same pattern you had for derivatives that you know well, that you're taking the derivative of something, you have a constant, multiply the coefficient, multiply, that it just follows along with the problem. Same thing for integrals. So this is 3x to the 1/2. And this is, I'm gonna write this is kind of 2 times, you don't have to write it this way, but this is 2 times 1 over x cubed. Or sorry. 2 times, yeah, actually, this is a good way to write it. So 2 times x to the -3. And then I'm gonna work the pattern for power functions for each of these parts. So x cubed, I bump it up to a 4 and then I divide by 4. So this gives me 6/4 x to the 4th power. 1/2, I bump it up to 3/2 and then I divide by 3/2. So let me write that out. 3 x to the 3/2, and then I'm going to divide by 3/2. And then -3, I'm going to bump it 1 up to -2 and then divide by -2. So plus 2 x to the -2 divided by -2. And then we're just going to work out all the fractions, whole numbers, just kind of all the fraction work from there, basically. So 6/4 reduces to 3/2. So what I end up here, and sorry, plus c, plus our constant. So I end up with 3/2 x to the 4th. Fine enough. When you do 3 divided by 3/2, so this, especially because we're in a calculus class, you guys have taken the previous classes. So some of this stuff I'm not going to write out each step just because you've seen it, you know how to do it, especially at this point. You guys are in Cal 2. You know how to manipulate fractions and kind of work with that. So 3/2, I'm going to flip that. So it's going to be 2/3, and I'm going to multiply it by the 3. So basically what happens is the 3's cancel out. So you're going to end up with -2 x to the 3/2. And then 2 divided by -2 is -1, so you're going to end up with -x to the -2, all plus c. And this is my integral. And again, I also can write this with the fraction power and the negative power reinterpreted by what they mean. So 3/2 x to the 4th -2 square root of x cubed. And then -1 over x squared. So both of these say the same thing. Both of these are correct. Good. All right, so this is, we've done actually a bunch of integrals to this point in all power functions. So again, like I was emphasizing, power functions, that pattern for power functions gets you a lot of different types of functions. It enables you to take the derivative or the integral of a lot of types of functions. But it doesn't get you everything. So we've looked at polynomials, we have some radical functions, and like I said, some really simple rational functions. But we haven't looked at any trig functions, right? And there's just some other functions that we haven't touched. And so what I want to do is I want to go back, just like I did at the beginning, and we kind of talked about the derivative power function and we worked it in reverse for an integral. So I want to go back and talk about some other derivatives that you know how to take from Cal 1. And then we're gonna look at it in reverse, and that'll give you a pattern for integrals, and we'll be able to do that with integrals. So, let's see. So some other derivatives that you guys know how to do. Actually, so let me work this. So I want to go to some trig functions. So going back again to your Cal 1 class, what is the derivative of sine? And if you forget, there is a table of derivatives actually in the front of this book. So if you're looking at the ebook, you have that pulled up. You can find there should be like a front appendix or something like that, or an appendix that has derivatives. So in case you forgot these, but what's the derivative of sine? That's cosine. Now, what's the derivative of cosine? That's going to be negative sine. And then now that you kind of know that, so if you know the derivative of sine is cosine and derivative of cosine is negative sine, what's the derivative of negative sine? So the negative would stay, but this derivative of sine is cosine u, so you end up getting negative cosine. And then what's the derivative of negative cosine? So if you've never seen it presented this way, so again, you guys know how to do all these derivatives from the previous class, but your teacher may not have presented it this way, but derivatives involving sine and cosine to me, when I was thinking through them, the cool thing is they end up being cyclical. They end up being circular. So we just said the derivative of sine is cosine. So what I'm doing here is I'm just basically showing you that the derivative of sine is cosine. And the derivative of cosine is negative sine. So I think of it literally like a circle, like a plot. But then the fun thing here is, so then when I go to take the derivative of negative sine, so again, like we just talked about, the negative is really just a coefficient, so that stays in front. And we know the derivative of sine is cosine. So the derivative of negative sine gets you to negative cosine. And then when I do the derivative of negative cosine, again, the negative is just a coefficient that stays in front, but I know the derivative of cosine is negative sine. So negative sine is positive sine. So the derivative of negative cosine gets you back to sine, and then you would just keep going around the circle every time you take a derivative. So the derivatives of sines and cosines are actually related to each other in this nice little circular pattern, and that's a really good way to remember and kind of memorize those derivatives. Now, again, integrals are just the opposite of derivatives. It's the same action, but in reverse. So that means if I want to take the integral, for instance, of sine, instead of going forward to cosine, I'm going to go back to negative cosine. And if I want to take the integral of cosine, I'm going to go backwards to sine. So literally, when you take the integral, all you do is take this forward diagram and just move your way backwards around it. So that means I almost don't even have to write it over here, but I do want to write it. So these are sine and cosine. Actually, I mean, honestly, don't even need a title for this section. You can see exactly what's done. So for an integral, the way this is going to work. So, I mean, honestly, we're going to write the same thing, but we're just going to write the arrows in reverse order because that's really what's happening. Cosine x, sine x, negative cosine x. For the integrals, you just go in reverse order. A little more long here. There you go. And that's your integrals for sine and cosine. Now there are other trig functions that you guys know that we obviously deal with. So let's look at some of the other trig functions that you can take derivatives of. Should I get this right? Well, so we've dealt with sine and cosine. Couple other, so let's look at a couple other trig functions. Uh, sure. A couple other, let's look at tangent. And I want to take the derivative of tangents. Now, what is the derivative of tangent? Actually, just to give some variety, let's go down numbers on this. The derivative of tangent, if you look back or if you remember that, is secant squared. So that means if I'm doing an integral, so the interesting thing about this now actually, so kind of on that last example we did the derivative of sine, I gave you cosine, and I basically was curious. I was like, well, let me keep doing that forward. What's the derivative of cosine? We ended up with this nice circle. Let's see, what is the derivative of secant squared? And the problem with this is actually something that's, give me a second, it's not that we can't do, but it's very hard to do. So you would assume that the other trig ratios kind of have some sort of simple relationship like this, and unfortunately they don't. So the derivative of secant is secant tangent, but once you do squared, you end up having to do kind of what they call, or if you remember, you have to do the chain rule. But the problem with this is there's no substitution you can use. There's no extra piece here that you can actually use the chain rule. So we end up, I'm pretty sure secant squared is maybe one of these that ends up as a weird 1 over a square root. But other than that, basically it doesn't have a derivative, or at least an easy derivative. So essentially the line ends here. You take the derivative of tangent, you get secant squared, and that's kind of it. And give me 1 second. Let me pause. Need to go to the bathroom. Right, so correction, actually, we want to talk about the secant squared again. Sorry, guys. So I mentioned it kind of would be hard, or you would need chain rule, but you don't have the extra piece. I was actually thinking of something we're gonna be doing with integrals. So I was thinking the opposite process. So this can be done with chain rule. So let's do some work really quick. I'll kind of figure out which pieces we kind of want to keep here, which not, but all right. So if we want the derivative of secant squared, we already used the chain rule, so we're thinking of secant is sort of our function inside. We're placing it in an x squared function. So first we need the derivative of secant x. So another thing that we want to mark here is what is the derivative of secant. So that's another one that you guys again hopefully remember from calc. But if not, just go ahead and look that up real quick. But what is the derivative of secant x? Good. The derivative of secant x is secant x tangent x. So then if I wanted to do the derivative of something like secant squared x, then the chain rule says that this is going to be 2 times the derivative of secant tan x, or derivative of secant x. So the derivative of this would be 2 secant x tan x. So what I was trying to say with sort of the derivative of secant squared is notice that unlike sine and cosine, it doesn't sort of take us back. It doesn't sort of take us back to tangent x. It doesn't basically take us in a circle. It basically gives us a more complex answer from there. So it kind of attacks the tan x onto it. And if you kept taking the derivative of stuff like this, it would actually do a similar thing. So instead of returning onto itself like sine and cosine does, it just keeps adding more pieces to this So because of that, just when I'm gonna talking about the derivatives here, we don't end up with a circle when you're talking about tangent or secant, but I'm at least gonna note these. These are the ones that we need to remember, that tangent of x derivative of tan is secant squared, derivative of secant is secant tangent. So that means, again, my integrals work in reverse. So for my integral, it's going to be the reverse. We're going to be able to take the integral of secant squared. And that's going to give me tangent of x. And we're going to be able to take the integral of secant x tangent x. And what's the integral of that going to be? Good. That's going to be secant x. But notice that means that, a good question is, what is the integral of tangent x? So again, because these don't go in a circle, sine and cosine are kind of like a closed loop, whether you're doing derivatives or integrals. But then the interesting thing with the integrals is that because tangent and secant aren't a closed loop on their derivatives, then I can do the integral of secant squared, but this doesn't tell me how to do the integral of tangent x. And I can do the integral of secant x tan x, but this doesn't tell me how to do the integral of secant x. So in a later part of this course, we'll kind of come back to taking the integrals of these. But basically what I'm saying is, the interesting thing is that two of your basic functions, tangent x and secant x, simple functions, are not so simple. Taking the integral of one of them is not a simple pattern. It's not so simple. Whereas sine and cosine are, and again, it's because sine and cosine, when you take the derivatives, end up in a loop. So when you take the integrals, you also end up in a loop. They all kind of go back to each other, but not so with tangent secant. And also not so with then cotangent. So we'll do another row here for cotangent. I really need to shorten this up. There's one other thing we got to look at after this, but for cotangent and cosecant, I'm writing this backwards. So yeah, let's shorten this up. So when I do the derivatives here, the derivative of cotangent is negative cosecant squared. And the derivative of cosecant is negative cosecant cotangent. Notice the patterns here are very similar, or exactly similar. So if you didn't notice that before in your Calculus 1 class, hopefully this makes it, you see it here, this makes it not only pretty obvious, but hopefully it's pretty cool. So hopefully it's kind of a cool pattern to see, that derivative of tangent is secant squared. So just like that, derivative of cotangent is negative cosecant squared. So basically the co gets the negative in there. The derivative of secant is secant tangent. So the derivative of cosecant is negative cosecant cotangent. So same pattern. And then we can literally read these patterns in reverse, and voila, we have our integrals. So the integral of negative cosecant squared, let's go down, is cotangent. And the integral of negative cosecant cotangent is cosecant. But again, what I want to mention is that means that if we want to take the integral of cotangent, it's not simple. Cotangent is the end of an integral, not the beginning of an integral. So we don't know what that is yet, and we don't know what the integral of cosecant is yet either. So again, in later sections we'll get to that. But notice this at least, in terms of both derivatives, but then integrals, covers a lot of our basic trig functions. We really have two more sets to look at. All right, so pretend that this is continuing, but we're going to continue it up here. So I guess let's just write it out. All right. All right. So what are some other functions or some other pretty easy classic derivatives that you figured out in this first class? And so some of the other ones are, I guess the only good thing about this is sort of in the zone. It's not a power function, but it's in the zone of the power function. So for derivatives, one of the things you figured out is if you take the derivative of the natural log of x, what does that give you? That gives you 1 over x. Which means then we take this process in reverse, and that tells us that the integral of 1 over x is the natural log of x. Now, this doesn't tell us how to take the integral of natural log. Again, we'll get to that in a later part of the class. But the surprising thing is natural log, even though it's a simple function, does not necessarily have a simple integral. But something like 1 over x, which is, remember, this is really x to the negative 1 power. So if you think about it, what this at least does help us do is if I'm trying to take the integral of 1 over x, you can rewrite that as x to the negative 1 power. And then if you think about, now that is a power function, but if you think about using the power function pattern, the one problem with it is that we'll see it actually fails in this one place because to take the integral, I'd have to do negative 1 plus 1, but what's negative 1 plus 1? That's 0. So you'd end up with x to the 0 power. And x to the 0 power is 1, so that's actually fine. But then you would have to divide by 0. Can I divide by 0? So that power function pattern, the one place it fails is trying to take the integral of x to the negative 1. Because I end up dividing by 0 and I can't do that. But because the derivative of natural log of x is 1 over x, or x to the negative 1, I now know that the integral of 1 over x is natural log of x. Basically, this kind of plugs the hole in the one place the power function pattern is missing a result, or that it doesn't work, basically. That's actually, honestly, the way I think about it. The power function, I actually think about in my head like a ladder. So essentially x raised to whatever power, right? But the powers are just rungs on the ladder. And the problem is, if you're at negative 1 on that ladder, when you try to go up, when you try to integrate, you get to 0 and you can't divide by 0. So there's one rung on that ladder that the power function doesn't work on, that you're missing, and it's x to the negative 1. But we now know what that is. So the integral of 1 over x, or x to the negative 1, is natural log of x. And by the way, if that helps you, that's actually, again, the whole power patterns with power functions thing. Whether you're doing a derivative or an integral, that's actually how I think of it in my head. I just think of it as a ladder. So whatever the power is, if I'm taking a derivative, I'm moving down that ladder 1 power. If I'm doing the integral, I'm just moving up 1 power. And that, especially if you're more of a visual person, that actually might really help you just very cleanly, fastly, efficiently be able to do derivatives or integrals on a power function. All right. So this plugs a hole in the power function pattern. Let's see. And then the only other thing that I can think of right now, at least, is when we're doing derivatives, we want to take the derivative of e to the x, right? But what's the derivative of e to the x? To remember that it's the one function, it's the only function we have that the derivative of e to the x is just plainly e to the x. It's kind of beautiful. So e to the x, in some sense, if you think of it even in terms of a graph, it's like basically the one perfectly balanced function. The slope at every point on that graph actually equals the y value at every point on that graph. Amazingly, and it's the only function that does it. So again, if the previous teacher didn't kind of posit it to you that way or give you that picture of it, or you can explain it that way, that's actually what's happening. The derivative of e to the x is e to the x, but what that means is the slope at every point is actually the y value, and it is the only function that we have, the only function ever that does it. So it's sort of like a center point, a center function. You know, like if you thought of this weird picture of not a graph of points, but a graph of functions, then, and the action in that graph is derivatives, then in that graph, e to the x would be in the center. It would be where the x and y axis. So anyway, so it's kind of a center function. But more importantly, if the derivative of the e to the x is e to the x, then if I take that backwards, that also tells me that the integral of e to the x is also just e to the x. So we now can do derivatives or integrals with x to the negative 1. We can do derivative integrals with e to the x. And that covers a lot of functions. So a lot of your simple derivatives that you know, you turn them around, and now we can do integrals with a lot of simple functions that we know. So I want to finish out this lecture. Now that we have some other, reminded ourselves of some other derivatives and figured out the integrals that come from that. Let's do some simple, let's do some simple integrals using those other patterns we know, or at least that we figured out. So let me go find those problems really quick. Then we gotta do, then we gotta do that type of problem. Well, don't have to. Don't have to. And man, we still have to do that type of problem. Man, it's just, there's too much in one section here. Like, do this annoying thing where they want to have every section spiral to 2 classes later, and you don't really need to do that. Don't do that problem. Don't do that problem. Maybe that problem, sure. We should look at something like that. I just need these lectures to not take so long to do. Let me put the problem back. So let's do, where was that? No, was that 8? So the integral of, let's spice it up. Let's do 3 secant squared theta minus 2/3 sine theta d theta. Do that integral. Let's do it. All right, while I'm figuring out these, let me pause. Okay, there we go. Let me turn the camera so you guys can see all these problems, but nope, wrong way. There we go. All right, so let's look at some problems like this. So like I said, 9 is the integral of 3 secant squared theta. We have, give me a second, let me just change one of these. I didn't realize there's secant squared, 2 of these. Sure, let's make this, actually, yeah. Let's make this minus. And let's make this cosecant cotangent. That works fine. All right. So 3 secant squared theta minus 2/3 sine theta. The integral of 2 cosine x minus 5 e to the x, and the integral of 4 over x minus square root of 2 cosecant x. So again, just mixing some pieces together that come from all of these patterns we just looked at for integrals. So the thing is, I'll actually want to leave you then to go ahead and see if you can run through this. So you guys have the patterns, easy enough. You're literally just working your way backwards from your derivatives. So you pause, I'll pause, and then we'll come back and work through them. All right, sweet. Let's knock these out. So starting with 9, again, taking the first piece, you have secant squared, and you're doing the integral, so you're working away. Again, I really actually think a lot of these like ladder. So except for sine and cosine, because they're a circle. I'm working my way back up the ladder. If I work my way back up to the ladder, where do I end up at? Good, tangent. And again, notice that 3 is just a coefficient, so it just tags along for the right. So my integral then is 3 tangent theta. Then we with sine theta, now I'm not working on a ladder, I'm working on a circle. I'm starting at negative sine theta, and I gotta work my way back around the circle. So when I integrate negative sine theta, where do I end up at? Good, I end up at cosine. So this is gonna end up as plus 2/3. Again, the coefficient just follows cosine theta. All of this plus c, and we are grading. We have our function. All right, so then on 10, same deal. So on the first part, we're starting with cosine. When I integrate from cosine, where does that get? That gets me back up to sine. So this is going to be 2 sine of x. And then e to the x, when I integrate that, where do I end up with? Good, just e to the x. So I'm treating not just the 5 now, the negative, I'm basically treating this as a -5. That's still just my coefficient. So I end up at -5 e to the x plus c, and I got it. And then our last problem here, so I'm integrating, first of all, 4 over x. So notice that again, that you can think of this as 4 times 1 over x. So that's that 4 is really a coefficient. So I'm gonna have a 4. But then the integral of 1 over x, what is that? Good, that's natural log of x. For reasons that I don't want to get into for the moment, you technically have to put the x in absolute values. This relates to kind of domain restrictions between the one over x function and the natural log of x function. And I just don't want to get into a ton of that right now. But just know that when you do the integral and you end up with a natural log, you have to put whatever was in here and absolute values. But otherwise, we're good, same thing. And then here, notice that, so I have cosecant x, cotangent x. The integral that we talked about over here has a negative with it. So one thing to notice here is that it has the negative with it. So the integral of negative cosecant x, cotangent x is cosecant x. So you, unlike previous on 10, where I just carried the negative down, this negative has to go with the cosecant cotangent x. It doesn't go with the coefficient. So I want to carry that with it. And what is the integral of negative cosecant cotangent x? Good, that's cosecant x. It's positive cosecant x. This is going to be plus square root of 2 cosecant x. And again, notice that square root of 2, it's square root, but it's not square root of x, right? So it's not a power function, it's just a coefficient. It's a fancy coefficient. Square root of 2 is just a number. So I'm going to carry that with it. Plus c, and I got it. All right. So in terms of all these kind of simple integrals, you guys can handle all this section. So 5-1. There's one other type of problem in this section that I want to do one problem on, and then we're actually going to be done. So I want to circle back to the beginning of this lecture. I was talking about one of the ways that you write these problems, instead of writing them in this general, sort of abstract integral form, they would write a differential equation for you. So we're going to look at some problems where they want you to solve the differential equation. So the same thing, they want you to take the integral. They're also going to give you what's called an initial condition, so that you can figure out what that c value is, what that initial coefficient is. So let me just write a problem up here from the book, and we'll look at how to do it. Really can only do one of these. Sure. So let's look at this one. The last. So they're going to say that g prime of x doesn't really matter. It's 4x squared. And they're also going to tell you that g of -1 equals 3. Make sure I get the numbers right there. So we don't end up with, these are awesome, but so we don't end up with crazy fractions. So this is what I gave you to begin with. They asked you to, so what they're going to do is ask you to solve that differential equation. You're going to give them an answer just like this. You're going to integrate it, you give them the function plus c. But notice by giving you this, they tell you now not anything about g prime, but they're telling you on g, on the solution that you're going to get, we now know an extra bit of information. We don't just know what g is. We know that g of -1 equals 3. When you plug in -1 to that, whatever that solution is going to be to this, you're going to get 3 out for y. So because of that, we're going to be able to do a little more extra work in finding our solution. So their overall goal still is to find the solution. They want you to find what g is. But before, when we solved it, we had this plus c at the end. We had this sort of constant that we didn't know what it was. So we know the solution, but there's still a little bit of generality there. You'll see this allows us to be hella more specific, or just be exact and more specific. So the first thing then is I'm going to take the integral of 4x squared and just figure out what the general solution is here. And the general solution, so 4x squared, so just kind of follow me through this. It's the power function, so I'm going to bump that up to 3 and divide by 3. So my general solution, so g of x it's gonna equal 4/3 x cubed plus c. Just doing the general solution. But like I said, now we know something extra. So before this would have been our answer, but now we know something extra. We know g of -1 equals 3. So now what I'm going to do is I'm going to take this info and plug it into this solution I just got. So g of -1 equals now 4/3 times -1 cubed plus c. And I know that that equals 3. So then what I'm going to do is now notice that I can solve for c. And now I don't have to write the solution with the c. I can write it with an actual number. And I can figure out what that constant is. So we're going to do that. So -1 cubed is a -1. So this ends up as basically, I'm going to rewrite the order here. C minus 4/3 equals 3. And then I'm going to add 4/3 to both sides. And what that tells me is C equals 3 is 9/3, so C equals 13/3. So then I'm going to come back over here and just plug that in, tap that into my solution, and I now have the exact solution for these. So they call these initial conditions. So literally what they're saying is, and this language really comes from physics, but literally what they're saying is for the initial function, these is one conditional in one of the solutions to that actual function. And that allows us to pin the function down to its exact solution, the constant known. So 4x cubed plus 13/3, and you got it. That is the solution to the differential equation. All right. So that'll get you everything for 5-1. And you'll see, I mean, it's also the introduction you need. You guys know the way math works. So it's the introduction you need really for all the sections, especially this week and going through the course. So start with this, work 5-1, and then watch the video for 5-4, and we'll start it and we'll get on to the next one. So when we come back for 5-4, like I said, this was my presentation of integrals in terms of inverses. We're going to go back and look at integrals. We're going to show one of the uses of integrals, but also just the main reason that integrals, like how it came up. So like I said at the beginning of the lecture, they really came up because we were trying to solve this ancient problem of how do you find the area under the curve. So we're going to look at integrals as an area under the curve on the next lecture. I'll see you then.